So in this lecture, we'll look at some options to apply regression to time series data, and we'll consider the merits of alternative approaches. So essentially, we're imagining data where we have several observations over time and we're trying to predict the next value. And we'll introduce the concept of autoregression in order to solve time series regression problems. So here we have a prediction problem like the following. We're given a sequence of real valued events, and we'd like to predict the next values in those sequences as accurately as possible. So looking back to our regression lectures, we saw this example of sequences of PM2.5 or air quality measurements that were taken hourly. Given this sequence of recent measurements, could we predict the next value in the sequence as accurately as possible? So imagine we're given a time series x1 to xn of real valued observations. Can we try to predict the next value in the sequence as accurately as possible? So before we look at autoregression, I'll look at some very simple techniques to try and solve this problem. The first is what's called a sliding window or a moving average. So if we'd like to predict the next value in a sequence, can we just look within some window of a fixed length and compute an average? So imagine you had data that looked like this. These are your observations over time. If you'd like to predict the next value as accurately as possible, one technique for doing so might simply be to look at a window of fixed length of previous observations and then just compute the average of the values within that window as an estimate of your next observation. That's a reasonably simple, though fairly sensible idea. All we're really saying is that recent values should be fairly predictive of the next value, but there could be some noise. So rather than just looking at the most recent value, we'll look at several recent values and take their average. All right, so that's called the moving average or sliding window. So if we're trying to predict data point xm plus 1 from the first m data points, all we would do is the following. We look in a sliding window of length k. So we'd look at observations xm down to xm minus k minus 1. Okay, that would be the k previous observations compared to the one we're trying to predict. And we would average those, so we would divide by k. So this turns out to have an efficient dynamic programming solution rather than computing this prediction for every single value in our vector. So really what we have to do to compute the next value of the sliding window is just peel off the oldest value and add on the new one. So just to draw what that looks like, if we had a sequence of values over time, we had the previous estimate from a sliding window we'd computed. To come up with the next estimate, it would be basically an overlapping sliding window. So all we have to do to compute the next estimate is peel off the oldest value and add on the newest value. And that's what's happening at the equation in the bottom of the slide. Okay, that's a pretty reasonable idea. All we did was take values within some window of fixed length and we averaged them. What can we do that's a little bit more sophisticated? So one option might be to weight points according to their age. We might think if we're trying to predict the next point in a time series, the most recent point might be somehow more relevant than less recent points. So we'll still try to apply the same idea of averaging several recent points. We'll just use what's called a weighted average. It gives more importance to recent points compared to older ones. So we're essentially doing the same thing with our sliding window. But rather than that sliding window being a rectangle, it will somehow be some, say, linearly decaying weighting function, where the most recent point is the most important and the point k steps back is the least important. All right, so we can write down the equation for that weighted average fairly straightforwardly. Again, we're looking at the k previous points to make the prediction for xm plus 1. We also have, though, a weighting expression which says how important is each point. And we're going to have the largest weight of k, for the most recent point, down to the smallest weight, a weight of 1 for the point k steps back. The other feature we have is we can't just divide by k to get the average. Because it's now a weighted average, we have to divide by k choose 2 in the denominator of that expression, which if we expand it out, is just the sum of all values of k from k equals 1 to capital K. So really, we're just saying what is the sum of all of the weights we're using to compute this average. All right, a third method, which is conceptually doing roughly the same thing, is just to use an exponential weighting scheme. So we'll weight the most recent points exponentially higher than the oldest points. The advantage of this compared to this linear weighting scheme we used previously is that we can essentially remember every point throughout history. They just have exponentially decaying importance. So now our weighting function would somehow look like this, where we had an exponential decay gradually trailing off to 0. And although that sounds more complicated, it's actually very, very easy to compute. We just start with our prediction for x2 being equal to the first value, x1. And then after that, the prediction of our next value is always going to be alpha times the previous observation plus 1 minus alpha times the previous prediction. All right, so just to compare and contrast those three methods, we saw sliding windows, we saw linear decay, and finally we saw exponential decay. A more complicated model, and to finally introduce time series regression, would be to say, rather than having all of these models which define weights using some predefined scheme, why can't we just learn the weights directly? So why can't we write it down using a regression problem? We have some coefficients theta, which tell us which of the previous k observations might be the important ones and which are the unimportant ones. So we could then fit this model using some least squares equation, just like we did in the regression in Python lecture. And this procedure will be called autoregression. So the value of this type of model is that it's going to allow us to capture periodic effects. For example, if we were trying to predict website traffic, certainly we would say a good predictor for website traffic is yesterday's website traffic, but there might be things like periodic effects. Maybe the best predictor of website traffic is actually whatever the traffic was exactly 1 week ago on the same weekday. Or if it's a holiday, maybe the best predictor of website traffic is whatever the traffic was exactly 1 year ago. It might not be just that the most recent point is useful for prediction, but it might be some weighted combination of different previous points. And this regression technique is going to allow us to determine which of the previous points are predictive and which are not. So just to summarize these concepts, we've introduced the problem of time series prediction or autoregression, and we've compared various techniques to solve time series prediction with and without machine learning. So on your own, I would suggest coming up with different types of data where these different models would be useful or work better than the others. So sliding windows, linear decay, exponential decay would be an appropriate model for different types of data sets. Can you try and come up with which ones? And in the next lecture, we'll try and put some of these ideas into practice by seeing how we can implement autoregression in Python.